We're now going to look at tidal forces. So let's consider a lighter body, such as Jupiter's innermost Galilean moon, Io, in orbit around a more massive body, that is Jupiter. So, as you can imagine, these tidal forces tend to stretch Io across its middle. Now, the inverse square nature of the force causes the gravitational pull by Jupiter on Io's near side to be greater than on its far side, and you can see that in the picture on your screen at the moment. And this is equivalent to two equal and opposite forces acting on the moon's near and far sides that tend to stretch and elongate Io, as shown in the a bit of exaggerated diagram on the right. It's important to point out that Io causes a similar but weaker effect on Jupiter. They are equal and opposite forces. Now let's apply these ideas to the Earth-Moon system. And the Moon exerts similar tidal forces on the near and far sides of the Earth. As with Jupiter's effect on Io, this is equivalent to two equal and opposite forces pulling on the Earth. These have the effect of creating two tidal bulges in the oceans on the parts of the Earth facing towards and away from the Moon. As the Earth spins, parts of the coast experience these bulges as the twice-daily high and low tides. The Sun's gravitational pull also contributes to the tides at full and new moon, when the Sun, Earth and Moon are aligned. Particularly high and low spring tides occur. In between these times, close to when the Moon is half full, the Sun and Moon's tidal forces act at right angles to one another to produce neap tides, whose height variations are much lower and less dramatic. Now, a second consequence of the gravitational pull by the Sun and Moon, this time on the slight bulge around the Earth's equator, is the slow wobbling or precession of the Earth's axis, which we've already talked about. Evidence of this axial precession includes the changing pole star, and I think I might have mentioned that the precession rate is about 1.4 degrees per century. The changing locations of the equinoxes, the points where the ecliptic crosses the celestial equator, and these are slowly drifting westwards, so the first point of Aries that marks the spring equinox is no longer in the constellation of Aries, but rather in Pisces and going towards Aquarius. The misalignment of ancient monuments and temples. Many such structures were carefully aligned to particular stars. You can think about the pyramids, for example. And by knowing the rate of precession of the Earth's axis, as I said, about 1.4 degrees per century, archaeoastronomers can determine the approximate dates of their construction. Now, let's talk about eclipses a little bit. It's an amazing cosmic coincidence, of course, that the Sun and Moon appear to be the same size. Both angular diameters are roughly 0.5 degrees. Now, when the Moon passes directly in front of the Sun, it obscures light from the photosphere to produce a stunning total solar eclipse for observers in the dark shadow or umbra on Earth. So obviously I put a range of pictures now. Have a look at those. Now, during totality, the sky darkens and some stars can be seen. The temperature drops and the Sun's corona can be seen. Just before and after totality, small bright spots of sunlight caused by the Sun's rays shining through valleys on the Moon are visible, and these are called Bailey's beads. Progress, and when only one is visible, this is known as the diamond ring effect. Now, solar eclipses occur at new moon and last for a few minutes. If the new moon obscures just part of the Sun, the observer is located in the penumbra. Then the Sun appears to only have a small bite out of it, a partial solar eclipse shadow. They occur at full moon, and during totality the moon is copper rusty red in colour due to predominantly red light, of course, refracting through the Earth's atmosphere. The blue light has already been scattered and illuminating the moon. Once again, key points in the eclipse's progress are described as first and to fourth umbral contacts. Whereas the time interval between second and third contact is only a few minutes for a solar eclipse, the time interval between second and third umbral contact for a lunar eclipse is much longer, up to 3 hours, because of the larger size of the Earth's shadow compared with that of the Moon.
In about 240 BC, the Greek astronomer and mathematician Eratosthenes calculated the circumference of the Earth within a margin of error of just 17%, using only his knowledge of the angle of elevation of the Sun. He noted that on the 21st of June, objects in Suene had no shadow at noon, because the Sun was directly overhead, whereas in Alexandria, 800 kilometres away, objects did cast a shadow. Eratosthenes then used the Sun's angle of elevation in Alexandria to calculate the circumference of the Earth as follows.
If we extend these two sticks until they get to the centre of the Earth, then we have created an alternate angle which must be 7.2 degrees. And if we know the arc length, which was measured at 5,000 stadia or about 800 kilometres, we, using simple ratios, are able to work out an estimate for the circumference of the Earth at about 40,000 kilometres. Not bad for a mathematician with a stick, a sun and a brain cell.
Now, we don't know exactly how Eratosthenes measured the distance between Alexandria and Aswan, but some sources say that he employed an army of men to pace it out, and others that he counted the number of rotations of a wheel of a carriage that was driven between the two cities. I like that second idea, but I don't think it's true. Anyway, the relative diameter of the Moon compared with that of the Earth was determined by Aristarchus of Samos, and he observed a total lunar eclipse and assumed that a lunar eclipse was produced when the Moon passed into the Earth's umbra, and that the Sun was so far away that its rays were parallel when reaching the Earth, and also that the Moon's path took it through the centre of the Earth's umbra, which had the same diameter as that of the Earth. So this diagram I'm showing you now is incredibly important, and because if we take all these three assumptions I've just met, or introduce you to, Aristarchus showed that the diameter of the Moon divided by the diameter of the Earth is equal to the time interval from U1 to U2 divided by the time interval from U2 to U4, and that's incredibly important. It won't be mentioned in the GCSE examination, you just need to know that. Okay, so maybe I ought to show you an example of how we could use that when we're back at school. Aristarchus was able to calculate that the Moon's diameter was between 0.32 and 0.4 times that of the Earth. The correct value is 0.27 times that of the Earth. Now, combining this with Eratosthenes' value for the circumference and hence diameter of the Earth, it was possible to calculate the diameter of the Moon. Now, the Greeks then set about determining the distance to the Moon. Now, Aristarchus reckoned that when he held his thumb at arm's length, it was just able to cover the Moon's disk. Now, by measuring the width of his thumb and the length of his outstretched arm, Aristarchus obtained a value for the angular size of his thumb, and hence that of the Moon. A knowledge of triangles, now real trigonometry was yet to be invented of course, then allowed Aristarchus to calculate the Earth-Moon distance. A further ingenious method allowed Aristarchus to determine the relative distances of the Sun and Moon. He waited until the Moon was exactly in its first quarter phase and measured the angle between the Moon and the Sun. It is uncertain how Aristarchus measured this angle, but we do know that he obtained a value of 29/30 of a right angle, which equates to 87 degrees. Using his knowledge of triangles, Aristarchus determined the radius S divided by D. Now, I have to put a diagram up on the screen now to say what I mean by S and D. But anyway, he determined the ratio S divided by D to be between 18 and 20. The Sun was about 20 times more distant than the Moon. We now know that the ratio is closer to 400 and suggests that the error was mainly due to the difficulty in measuring angles when they were very close to 90 degrees. The Greeks knew that the Sun and Moon subtended the same angle. If the Sun was 20 times further than the Moon, the diameter must be 20 times larger. Knowing the diameter of the Moon from earlier calculations, the diameter of the Sun could then be calculated. It's very worthwhile trolling the internet for videos that make this arm and thumb measurements more clear. You will be asked about them.